Hi everyone, Mrs. Basega here. And whether you missed class today because of the SATs or you just want a video recap of the things that we did in class today, you've come to the right place. So I'm going to skip through lots of things that you can look up in the slides on your own, like this CAT scale, like our content objectives. At the beginning of class, I spent a few minutes reviewing velocity versus time graphs. I reviewed acceleration, how to get the area under a curve and use that to calculate change in position. And where I'm going to start off is after this video, because everything else you can just read straight from the slides. You don't need me to explain anything. Watch this video from Professor Brian Cox. He'll be explaining and introducing freefall. Actually, what he's doing is he's going to the world's largest vacuum chamber, and his goal is to come up with the actual free fall conditions. Normally, we can't do free fall on Earth because there's too much air in the way. And it's really, really, really hard to pump tons of air out of a place like a giant bunker or a building. And you certainly can't take all the air away from the planet. As a result, it's really difficult to get what's called free fall. It's this theoretical state of motion in which gravity is the only force acting on an object. It makes for very easy to draw free body diagrams because there's only one force. And a special thing to note about free fall that's very apparent from the video is in free fall, all objects accelerate at the same rate. That means if me and a pile of pennies and a bowling ball and a pillowcase all were going to fall the same distance, all of them would hit the ground at the same time in theory. We know that doesn't happen in practice because in practice there's air in the way. So something like a pillow would have a larger effect of air resistance than it would on a person, and I'd hit the ground first. Bad news bears. So you might notice this negative 9.8, that number is the same 9.8 that's in gravitational field, and that's for a reason, which we will talk about soon. So all objects in a gravitational field accelerate at negative 9.8 meters per second every second. What that means is if I do take like the apple, for instance, and I drop it from rest, it would start at rest and every second would travel faster and faster and faster in the negative direction. So let us add some things here. Let's say we have time versus velocity. An important thing to note then is that at 0 seconds of time, my object would start from rest. But after 1 second of time, it would now be going faster. It would be going negative 9.8 meters per second. At 2 seconds of time, it would be going negative 19.6. Notice that between each second of time, it's falling faster and faster and faster just in the negative direction. And my graph only shows 4 seconds of time, so that puts us to 39.2 meters per second down. All the velocities are negative. So I can always determine the changing velocity. I can always determine a velocity by simply taking the initial velocity, so taking my 0, and subtracting repeatedly the 9.8. So I'm subtracting repeatedly 9.8 to get to the final velocity. So if I had free fall from rest and it fell for 4 seconds of time, I could then get the final velocity of 39, which would end up being the height of this triangle, to determine the distance it falls by taking the area under the curve. That's why we did so much area under the curve the other day. Things you should know about this type of free fall is that it starts from rest. It travels 9.8 meters per second faster every second in the negative direction. And then that blue triangle, the area under the curve, represents the distance fallen. Since that area under the curve is below the x-axis, it is a negative distance, a negative displacement, meaning you end up lower in height than where you started. Other popular ones to be asked in free fall, there's 3 types that we'll do total. Type number 2 is a symmetrical problem. What if I didn't just take an object and like drop it from rest? Because that's boring and that's not what necessarily happens most of the time. Well, if I take an object and I launch it instead, like kicking a soccer ball or launching a rocket, something like that, this is a symmetrical problem. What that means is that it starts at some sort of positive velocity, accelerates at negative 9.8 meters per second for all of the seconds until it reaches a special point. That point is called the apex. The apex is right near. It's also right here in my picture. Things to know. At the apex, the ball has no vertical velocity. It's no longer moving up and down. See how the velocity is 0 on the graph at that point in time? The symmetrical part is that, well, notice it took 4 seconds to get to the top, so it will also take 4 seconds to fall down. Notice also that the area of the pink and blue, those represent the distance traveled to get to the top. That should be equal to the distance fallen, that's the blue. It's called the symmetrical example for that reason. So let's talk about the velocities. How do I solve this problem then? In this problem, let's say I start with a velocity. And at time 0, let's give it a velocity of, let's give it a velocity of 39.2 for reasons you'll see in a second. At time 1, that means subtract 9.8 from that. That means at 1 second, you're going 29.4 meters per second. At 2 seconds, you're going 19.6 meters per second. And if I just keep repeatedly subtracting, I'm going to end up eventually at time 4 with a speed of 0 meters per second. That means that apex occurs at 4 seconds. Right? But hey, the ball doesn't stop when it reaches the apex, right? So it's going to fall back down now. And now it's going to fall. It's going to go to negative 9.8, negative 19.6. Right? Can we figure out where we're going here? It's going to do the same velocities as before, but negative. Oh, we might have to use the space bar. There we go. And I notice it took 4 seconds to reach the apex, right? If it took 4 seconds to reach the apex, I expect that at 8 seconds, that it should have that same velocity that it started with, but negative. By the 8th second, notice that my velocity is negative 39.2, right? If I kept repeatedly subtracting 9.8, I'd eventually get 0 at the apex, right? Repeatedly subtracting, I'd eventually get 0 at the apex. I'd notice it took 4 seconds to get to the top. It would take 4 seconds to fall, and it would have equal velocity to start and at the end. The last possible thing I could ask you is the asymmetrical case, mostly because this is what normally happens in sports anyways. It's not normally an object that starts on the ground and ends on the ground. Maybe it's something like this, where it's an object that starts in your hand, it's thrown up in the air, and ends at the ground, so that the starting height and initial height aren't the same value. So, in an asymmetrical toss-up, notice it starts with some positive velocity. It travels upward. It stops at the apex, and then it falls for a larger distance. It spends more time traveling up than down. What this would look like in a velocity versus time chart is this would start at 19.6, subtract 9.8, subtract 9.8 so that it stopped at 2 seconds, and I'd keep subtracting 9.8 meters per second until I find its final velocity. In this case, it fell for 1, 2, 3, 4, 5, 6. It fell for 6 seconds after reaching apex. Therefore, its final velocity would be 6 times 9.8, or it'd be 0 minus 9.8 6 times. So it would be 6 times 9.8, which I don't remember off the top of my head. You can look it up. All right. So in the homework, you're going to try all 3 of those problems. Though you might see some questions, sneaky ones, talk about air resistance. So if you haven't watched this air resistance video yet, peek at that, and then check out the remaining notes on air resistance. For those, we're not ever going to have to solve big, scary looking equation here, unless you really want to. Right? Unless you really want to, you're never going to have to solve this equation, but you should know what it depends on, what it does to your object, and how to draw it in a diagram. Right? That is all, folks. If you could work on homework 2.3, free fall, that will be your next homework assignment, and we'll practice all the free fall stuff we did in class today. Bye.